Hello friends. Through this session, we will look at an alternate way of defining rational and irrational numbers. As you would recall, numbers can be classified as either imaginary numbers or real numbers. At the second level, we classify real numbers into rational and irrational numbers. The further classifications will be there as far as rational numbers are concerned. For now, let us focus on the classification of real numbers into rational numbers and irrational numbers. Throughout our school and in our earlier part of our education, we would have learned that rational numbers are numbers, any number which can be expressed in the form p by q, where q is not equal to 0 and p and q are integers, is called a rational number. So this is a number in the form p by q where q is not equal to 0 and p and q both are integers. It often makes us wonder, what exactly does it mean? What exactly does it mean for a number to be expressible in the form p by q where q is not equal to 0? On the other hand, irrational numbers are numbers which cannot be expressed in the form of p by q. Again, for the sake of example, all integers 1, 2, 3, etc., etc., these are rational numbers because they can always be divided by 1 and written in the form p by q. Similarly, fractions 2 by 3, 5 by 4, etc., these are also rational numbers. On the other hand, if I look at the examples of irrational numbers, the square root of 2, the square root of 3, the square root of 5, and so on and so forth, these would be irrational numbers. At the same time, pi and e, these are also irrational numbers. The question is, what is it that is different between these two categories of numbers, and how exactly do we say that these are rational and these are irrational? For our understanding, rational numbers are the numbers which can be represented on the number line, and irrational numbers cannot be represented on the number line with a precise point. And that is where probably the understanding of rational numbers would lie. How do we represent them on the number line? Suppose a number is, let's say, 8 upon 3. 8 upon 3 is equal to 3 to the 6, 2 plus 2 upon 3. In order to represent 2 plus 2 upon 3 on the number line, if I look this is as this is number line, this is point 0, this will go to minus infinity, this goes to plus infinity for values of x. This point is 1, this point is 2, this point is 3. If I have to count 8 upon 3, 1, 2, and then over here I need to take 2 by 3. For 2 by 3, I'll divide this range 2 to 3 in 3 equal parts. And having divided this into 3 equal parts, I will take 2 portions from here. So this becomes 2 upon 3. Overall, 1, 2, 2 upon 3. So therefore, this is precisely the point that will represent 8 upon 3. On the other hand, in the case of irrational numbers, because they cannot be written in the form p by q, finding a precise point on the number line will not be possible. Okay. Now let's look at an alternate way of defining rational and irrational numbers. If I look at decimals, decimals can be either terminating or they would be non-terminating. By terminating decimal, what I mean is, let's say 2.5. So it terminates at 5. 2.375. It terminates at 375. 2.56569. It terminates at 9. So those are a decimal which terminates at a certain point, that's terminating. On the other hand, a decimal that does not terminate, let us say if I look at 1 by 3, 1 by 3 is equal to 0.33333, which is, this goes on till infinity, which is represented as 0.3 bar. This is non-terminating. As far as the non-terminating decimals are concerned, they can again be classified as either recurring or non-recurring. By recurring, what I mean is, let's say in this case we saw that 0.3 bar, there is a bar on 3, 3 will keep repeating. If the number is 0.37 bar, so 373737, the pattern will continue repeating. A number in which a definite pattern keeps repeating over and over and over again, that is recurring. On the other hand, numbers in which there is no definite pattern in which the digits are appearing, those are non-recurring. And for sake of classification, if a number is terminating or recurring, then it is called a rational number. On the other hand, if it is non-recurring, non-terminating, then it is a irrational number. Let us now understand how to represent these terminating and recurring decimals in the form of p by q, so that they can be called rational numbers. Let us say I have to convert 0.3 into a fraction. In order to convert 0.3 into a fraction, this will very simply be written as 3 upon, after decimal there is only one digit, so therefore 1 followed by 1, 0. If it was 0.38, that would be equal to 38 divided by, there are two digits, so 2 zeros. So as far as terminating decimals are concerned, it is very easy to convert them into fractions. The problem comes when we need to convert the recurring decimals into fractions. Let us say I have to convert 0.73 into 0.7 with 3 has a, where 3 has a bar. Let us say this number needs to be converted into a fraction. In order to convert 0.73 bar into a fraction, there are two ways of going about this. One method, as would have been, as you would have studied, let us say y is equal to 0.73 bar. There is one digit repeating, so I'll multiply this both the sides by 10. Had there been two digits repeating, I would have multiplied by 100. Had there been three digits repeating, I would have multiplied by 1000. Depending as many digits which are repeating on this side, I multiply this both the sides by 1 followed by that many zeros. Here I am multiplying by 10, 10y is equal to 7.33 and so on so forth. Because 3 has a bar, so this will become 7.33 bar. The idea here is that once I have put 3 bar over here and 3 bar over here, and this is an infinite number of 3's, from that 1 3 added or subtracted, it will not make any difference. So we can write y is equal to 0.73 bar, 10y is equal to 7.33 bar. Now if I subtract the first equation from the second equation, I will get 9y is equal to 7.33 bar minus 0.73 bar. This is equal to 7.3 minus 0.7, which is equal to, so from here I can write 9y is equal to 73 minus 3, 66, 6.6. y is equal to 6.6 divided by 9. This decimal will disappear from here, this becomes a 0. So effectively y is equal to 66 upon 90, which can then be further simplified. Both the sides, numerator and denominator, are divisible by 6. So this is equal to 11 upon 15. So 11 upon 15 is the value of y. This is one method that will definitely give us the decimal to fraction equivalent. However, this can be a little tedious. Here is an alternate and a much shorter direct way of converting a decimal into a fraction. The number is 0.73 bar. I write 73, the number without any decimal or without any digits repeated, minus the non-repeating part of the decimal, which is 7, divided by as many 9's as the number of digits repeating. So there is only one digit repeating, so I'll put 1 9 over here, followed by as many zeros as the number of non-repeating digits. So this will be followed by 1 0. 73 minus 7 is 66, 66 upon 90, directly we get it from here. Again, I'll write this in a general form. Number without repetition minus non-repeating part divided by as many nines as the number of digits repeating. Here, because there is only one digit repeating, so therefore I put only one 9, and this is followed by as many zeros as the number of digits not repeating. Because there is only one digit that was not repeating, 7, so I put 1 0 here. Let's take a couple of more examples. Let's say y is equal to 0.73, 73 has a bar. This will become 73 minus, there is nothing that is not repeating, so nothing is required there. There are 2 digits repeating, so there will be 2 9s here. So this is equal to 73 upon 99. Similarly, if y is equal to 0.738, 38 has a bar. This will be equal to 738 minus, there is one digit that is not repeating, so minus 7, divided by, there are 2 digits which are repeating, so 2 9s, followed by one digit not repeating, so 0. So 738 minus 7, 731, 731 upon 990 would be your number. And so on and so forth. Like this, we would be able to convert any decimal into a fraction. The point being that because any decimal which is terminating or which is non-terminating but recurring, it can be converted in the form p by q. Therefore, these are rational. Numbers which cannot be written in the form p by q, where q is not equal to 0, are called irrational. One last point to highlight in this. The examples that we have written on the side of the irrational numbers, if we look at, let us say we have got a root 2 here. If I look at calculating the square root of 2, or if I look at calculating the square root of 3, or if I look at calculating the square root of 5, any natural number, the square root, where n is not a perfect square, it would be an irrational number, because when I calculate the square root of 2, I would not get any definite pattern of digits that would be repeating. It will be the digits, they will appear in random order. Because the digits are appearing in random order, therefore these are irrational. Also, if I look at the value of, I have put pi on this side. Many of us would say that pi is equal to 22 by 7. Now, 22 upon 7 is definitely a number in the form p by q, where q is not equal to 0. So therefore, pi and 22 upon 7, 22 upon 7 is rational, but we say that pi is irrational. The reason for this apparent anomaly is that 22 upon 7 is merely an approximation for the value of pi. 22 upon 7 is not the exact value of pi. That's why 22 upon 7 can be a rational number. It is definitely a number in the form p by q, where q is not equal to 0, whereas pi is a irrational number.